right, so good to see you. And today I plan to move on to the next topic in the course, which is equations of homogeneous type. Unless you have questions, comments, if you want, we can already review for the midterm, though I think it's too early. So what do you think?
I'm moving to this next part.
Okay, so then I'll jump straight to page 6. Yeah. So this is the topic of today's course, homogeneous first order or homogeneous type first order ordinary differential equations. And just a second. Yeah, so homogeneous type first order ordinary differential equations. And so in order to define these equations properly, we need to introduce the notion of homogeneous functions. So before that, so let's make this distinction between homogeneous type equations, which are first order equations and in general are nonlinear, and on the other hand, homogeneous linear equations, which are linear equations for which the source term is 0. So actually, yeah, so let's first define it and then let's give examples that show the similarities and distinctions between the two notions that have a very similar name. So the word homogeneous is the same in the name of both homogeneous type equations and homogeneous linear equations. So I have added the word dash type to homogeneous equations, especially, I mean, on purpose so that we can distinguish them at least by name. So first, let's define a homogeneous function. A homogeneous function of 2 or more variables is called a homogeneous function of degree n if for any t bigger than 0, f of tx, ty is equal to t to the n f of x and y. And the same is true if it's a function of more than 2 variables. So for example, f of tx, ty, tz is equal to t to the n f of x, y, and z. So homogeneous functions are in some sense related to polynomials in that they have a degree, but unlike polynomials, for homogeneous functions, the degree does not have to be a positive integer or an integer at all. So it can even be a complex number. So here are a couple of examples. So this is a polynomial. It is a homogeneous polynomial of degree 2 because all the powers x squared, xy, y squared are of degree 2. And in the case in which we have a product of both variables or whatever, more than one variable, then the degree that we count is the sum of the degrees of each individual variable. So the total degree. So here x squared has degree 2 because it is x to the second power. X times y has degree 2 because x is to the power 1 and y is also to the power 1. So the total power is 2. And y squared also has degree 2 because y is raised to the power 2. Same for x cubed plus 2x squared y. So it is homogeneous of degree 3. So again, it is a polynomial. So not all polynomials are homogeneous. For example, if we had x squared plus xy plus y, this would be an inhomogeneous polynomial because some of the powers would be of degree 2 and one of the powers would be of degree 1. But homogeneous functions need not be polynomials. So here's the next example. 1 over xy squared plus 1 over x squared y is homogeneous of degree -3, and it's most definitely not a polynomial because a polynomial only has non-negative powers. So this kind of more general function is called a rational function, which is the quotient of two polynomials. So this one has degree -3 because in the first term, x is to the power -1 and y is to the power -2. So the total power is -3. And likewise in the other term. This is also, so the next one, 1/x² plus 1/xy plus y squared is also a rational function. Again, it's not a polynomial. And again, it is homogeneous of degree -2. And at this point, I'm again going to draw your attention, as I think I did in the last course, that the word homogeneous is written with an E, and I mean with a second E. And if you write it as homogeneous, then I think it has a similar but very distinct meaning related to crystallography or something like that. So f of xy is equal to square root of x plus square root of y is homogeneous of degree 1/2. So again, the powers do not need to be entire. Here, both x and y are present with power 1/2. So the first term contains x to the power 1/2, so it has total degree 1/2. Second term contains y to the power 1/2, so it has total degree 1/2. And the sum of these terms of the same degree is again homogeneous of degree 1/2. And finally, a more trivial example. So f of x and y is 2x plus y is homogeneous of degree 1. So homogeneous of degree 1 means linear and with no constant term. So for example, if we had 2x plus y plus 1, it would not be a homogeneous function. Okay. So any question up to here? Right. Let's see if I missed anything. If not, let's move on. So, okay, so I think I said I was going to try to give an example of each of the 4 kinds of equations, which are homogeneous linear equations and of homogeneous type, or which may have one of these qualities but not the other, or which have neither. So let's do this on the board. So yeah, let's see here. So first, let's give an example of an equation which is both of homogeneous type and a homogeneous. But first, actually, let's define what a homogeneous linear equation is, because I think I haven't got to that point yet. So that will be more appropriate. So let's go back to let's go back and give the full definition, and then let me give these examples. Okay, so is this the right one? Yeah. So here are some examples of functions which are not homogeneous. So x squared plus y is not a homogeneous function because one of the terms has degree 2 and the other one has degree 1. E to the x plus e to the y is not homogeneous because e to the x is a transcendental function and it does not have degree. So only powers have degree, or combinations of powers. And here is such a combination of powers. So x plus y squared over x is homogeneous of degree 1. So x has degree 1, y squared has degree 2, and then 1 over x has degree -1. So the total degree of y squared over x is 1. So then both terms in this expression have degree 1. Therefore, f of x is a homogeneous function of degree 1. Let's see. So finally, we get to the definition of a first order equation of homogeneous type. Namely, an equation is of homogeneous type. So a first order ordinary differential equation is of homogeneous type if it can be written as y prime is equal to the quotient of two homogeneous functions both of which are homogeneous of the same degree. And now you can also notice, though I haven't written it, that the quotient of two homogeneous functions of the same degree is a homogeneous function of degree 0. So actually this is if and only if, so a homogeneous function of degree 0 is also the quotient of two homogeneous functions of the same degree. So actually I could have said in this definition that y prime is equal to, let's say, f of x and y, where f is homogeneous of degree 0. But I think that this definition is easier to, the definition that I gave here is easier to use in practice because it's easier to recognize when m and n are homogeneous functions of the same degree. And before we move on, so these equations are also often written in differential form. So the expression here is not equivalent to the expression here because there's a minus missing. It's should be minus m of x and y dx or something like that. But nevertheless, both are the general form of a homogeneous type equation of first order. So these are some examples. And let's see, actually, maybe I have already given here examples of equations which are both homogeneous and, I mean, both of homogeneous type and linear homogeneous equations, or maybe not, maybe they're on the next page, or if not, I'll give them. So let's see. Okay, the first example, y prime is equal to x minus y over 2x plus y. So here, x minus y is a homogeneous function of degree 1. 2x plus y is also a homogeneous function of degree 1. So this is a homogeneous type equation. And note that just by looking at it like this, it is pretty easy to tell whether it's going to be homogeneous or not, but we cannot really tell whether it's going to be exact or not. But you should test for exactness anyway. In what order you prefer, but you need to test for exactness anyway. And okay, what about this equation? Y prime is square root of x plus square root of y over square root of x plus y. So I'll use this opportunity to point out that square root of x plus square root of y is not in general equal to square root of x plus y. So here all terms have degree 1/2. And so both the denominator and the numerator are homogeneous functions of degree 1/2. So this is a homogeneous type equation. What about this one? So x prime minus y squared dx plus 2xy dy. So this equation is written in differential form. It is very clearly homogeneous, and it may yet be exact. So either this one or the one below it is exact. But I don't remember which one it is. Oh, it says here. So this one is both of homogeneous type and exact. So let's actually check. So if we denote x squared minus y squared by capital M and 2xy by capital N, then partial m over partial y is minus 2y, and partial n over partial x is plus 2y. So this equation is most definitely not exact. However, it is one of those equations that can be made exact. So it's definitely not exact, but it can be made exact, maybe by multiplication by 1 over x squared plus y squared quantity squared, or something like that. So the equation below it is already exact, and it is also homogeneous. So it can be solved both ways, and well, this will result in equivalent answers. Okay, so any question up to here? Let's see, has anybody else joined us?
Definitely not.
Yeah, I still only see the three of us. And all right, so these are some equations that are not homogeneous. just to tell the difference. So y prime is x minus y over 2x squared plus y. Here, the denominator, sorry, the numerator is a homogeneous function of degree 1. So x minus y is a homogeneous function of degree 1. And on the other hand, the denominator here, 2x squared plus y, is no homogeneous function at all, because 2x squared has degree 2, y has degree 1, therefore their sum does not have any particular degree. What about this equation written in differential form? So x squared plus y squared plus 1 dx plus 2xy dy. So here, again, the coefficient of dy is 2xy, which is a homogeneous function of degree 2. In fact, it's a polynomial. In fact, it's a monomial. And x squared plus y squared plus 1 is not a homogeneous function at all, because 2 of the terms have degree 2 and 1 has degree 1. Okay. I guess maybe it would make it easier if I pointed at the board, whatever the slides, but now let's move on to the next example that I actually wanted to give, like I said. Let's see. So, right, so I said I wanted to give examples of equations which are both homogeneous and of homogeneous type, or which possess one of the quantities but not the other, or which possess neither. So let's give an example of an equation which is both of homogeneous type and linear and homogeneous. So let's say y prime is equal to y over x. So this equation is of homogeneous type because both the denominator and the numerator are homogeneous functions of degree 1. So actually they're both monomials of degree 1. One is x and one is y. On the other hand, this is also a linear equation in y. So y prime, you see here, is present linearly. Y is present also linearly. The coefficient of y is 1 over x. And since there is no source term, or the source term is 0, as you prefer, this equation is linear and homogeneous. So let me write it. Actually, let me narrate it. So I think I've said enough. So what about an equation which is, let's say, of homogeneous type, linear, but inhomogeneous? So y prime is equal to y over x plus 1. I don't like this, so let's undo it. So y prime is equal to y over x plus 1. So as written, maybe it is not apparent that this equation is homogeneous, though I hope it is apparent. But in any case, we can rewrite it as y plus x over x. I mean, we can rewrite the right-hand side as y plus x over x. And now it is clear that this equation is of homogeneous type because y plus x is a homogeneous polynomial of degree 1, and x is a homogeneous monomial also of degree 1. So it is clearly an equation of homogeneous type. This equation is also linear if you look at the previous form. So because you see this is y prime is equal to 1 over x times y plus 1. So here 1 over x is the coefficient of y. The equation is linear both in y prime and in y, and in y prime jointly with y as well. But this has a source term, namely the plus 1. So this equation is actually inhomogeneous. So it is an inhomogeneous linear equation. but it is of homogeneous type. Let's see. Another example, let's say an equation which is a linear homogeneous equation, but it is not of homogeneous type. So let's say y prime is equal to, let's say, so I said linear and homogeneous, but not of homogeneous type. So let's say y over x plus x squared. So I'm not aiming for complicated examples. I'm just giving the simplest examples that come to mind. So this equation is clearly linear and homogeneous. So it is a homogeneous linear equation because you see it's linear in y prime, it's linear in y, and the coefficient of y is 1 over x squared plus x, and it has no source term. So it is a homogeneous linear equation. But on the other hand, this equation is not of homogeneous type because you see the right-hand side is the quotient of two functions, one of which is homogeneous of degree 1, but the other one of which is not homogeneous. Okay. So I think these three examples are enough. I mean, of course, there's also a third equation where the equation, a fourth situation where the equation is neither homogeneous, or whatever, nor linear, nor of homogeneous type. But I think these three examples should suffice. So do you have any question up to here?
No.
Okay, then let's move on. So now let's go back to the slides. All right. So let's see, make sure. Yeah, so yeah, I should have said this a while ago, but yeah, I have started recording the class and I will post the recording, this time with video, on the course website and on YouTube. So okay, so now let's move on. So for all homogeneous type equations, there is a solution method. So they are solvable algorithmically. The algorithm consists of a substitution, which is guaranteed to reduce these homogeneous type equations to separable equations, and then in solving the ensuing separable equation, and then in undoing the substitution and solving for the original unknown function y. So this is, by and large, the same procedure as for solving Bernoulli type equations, except that the substitution is different. And for Bernoulli type equations, after the substitution, we had to solve a linear equation. For homogeneous type equations, after the substitution, we'll have to solve a separable equation. So actually, for the homogeneous type equations, the substitution and the computations are slightly harder algebraically, but still it's just an algorithm. So let's see. So the substitution is always the same. Y of x is equal to u of x times x. So we, instead of the unknown function y, we use the new unknown function u, which is the quotient of y divided by x. It's also possible to make the opposite substitution. So it's also possible to make the substitution v is equal to x divided by y, but I think in that case, one has to solve a separable equation for x as a function of y instead of y as a function of x, or whatever. I mean, sorry, v as a function of y instead of u as a function of x. So if y is equal to ux, which is what we are using to solve this problem, then by the product rule, y prime is equal to u prime x plus u times x prime. And since x is the variable, then x prime is 1. So y prime is equal to u prime x plus u. So now let's prove that this substitution works. Hi, Alison, how are you? So now let's prove that this substitution works as claimed. So consider any homogeneous type equation, y prime is equal to m of x and y divided by n of x and y, and let n be the degree of m and n. So often n is an integer, but it need not be. So as I said, it can also be anything up to n, including a complex number. So, okay, this is our equation. Now, let's divide both the denominator and the numerator in the fraction by absolute value of x to the power n. So again, this makes sense in general when n is a complex number. So powers of non-negative real numbers are well defined when the exponent is well defined and uniquely defined when the exponent is a complex number. And let's see what happens. So because m of x and y is a homogeneous function of degree n, and because absolute value of x is a positive number, so we only want to do this when x is bigger than 0 or when x is less than 0. This method may not actually work at x equals 0. So extra care is needed at x equals 0, along the lines of what I told you about separable equations and so on. So here, suppose that we factor out absolute value of x to the n, then by the definition of a homogeneous function, m of x of y is equal to absolute value of x to the n times m of x divided by absolute value of x and y divided by the absolute value of x. And x divided by the absolute value of x, since x is a real number, x divided by absolute value of x can only be plus or minus 1. And again, this will not work when x is equal to 0. So we get m of plus or minus 1, according to whether x over absolute value of x is plus or minus 1, and plus or minus y over x, according again to whether x is a positive or a negative number. So if x is a positive number, x over absolute value of x is plus 1. If x is a negative number, then x over absolute value of x is minus 1. So same here. I guess 1 over plus or minus 1 is the same thing, plus or minus 1. Or whatever. So,
Professor,
yeah, go ahead.
you said the n is the power of m minus the power of n.
No, the n here is the common degree of both capital M and capital N. So capital M
Okay.
and capital N are both homogeneous functions of the same degree, lowercase m. Okay, so maybe it's actually good to point.
Thank you.
Let's see. Is it in here? Let's see.
I think it was on the past slide. I just missed it.
Oh, sorry. So let's see. Where, let's see, does this? Spotlight. I think spotlight is what I want here. So, okay, so I am pretty sure that you can see the spotlight now, right?
Yes.
Confirm? Okay. So, yeah. All right. So, let's see. So, because we actually do this separately for x bigger than 0 and for x less than 0, then in each of those two cases, it's either plus or 1 or minus 1. And it's either plus y over x or minus y over x. And the sign is the same. So it's either plus plus or minus minus. In either of those two cases, this is, so in either of those two cases, this is a function of y over x. So separately, when x is bigger than 0 and when x is less than 0. So we are left with just some function of y over x on the right-hand side of the ODE. So f y prime is equal to some function of y over x, where this function is given by this expression. So as stated earlier, it's capital M of whatever over capital N of whatever. And the choice of sign is the same both in the, I mean, in all four places, both in the denominator and in the numerator. So it's either plus, 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 or minus, 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 minus. But since there's probably some sort of discontinuity at 0 or whatever, so in any case, we have to solve it separately for x bigger than 0 and for x less than 0. So, I mean, the fact that we're dividing by x here, for example, it doesn't matter to us, or whatever. The fact that we have the choice of plus 1, whatever, plus 1x is bigger than 0 and minus 1x is less than 0 also doesn't matter to us, because in any case, we need to solve the equation separately when x is bigger than 0 and when x is less than 0. But in either case, the solution is the same and looks the same. So we don't need to solve it twice. So, okay. So, right, so the right-hand side of the equation is a function of y over x, which we have already denoted f of y over x. And so now we look again at this equation, y prime is equal to f of y over x, and we use the substitution that I announced already earlier. So we use the substitution, u is equal to y over x, which means that y is equal to u times x, and implies that y prime is equal to u prime x plus u. So making the substitution, y prime becomes u prime x plus u, and f of y over x becomes f of u. So now let's solve this for u prime algebraically, and this is a linear equation in u prime. We subtract u from both sides, and we get that u prime x is equal to f of u minus u, and then we divide both sides by x, and we get that u prime is equal to 1 over x times f of u minus u. So again, notice that something special will probably happen at x equals 0. So the case x equals 0 needs to be treated separately. So either way, if we avoid x equals 0, then we recognize that this is a separable equation. So u prime is equal to 1 over x, which is a function of x, times f of u minus u, which is a function of u. So it is a separable equation. And then we solve it in order to find u, and then using the fact that y of x is equal to u of x times x, after finding u, we multiply it by x, and we obtain y itself. Okay, so we have time for at least an example, maybe two. let's see. Okay, so, okay, let's have a look at this equation. I don't remember if I solved it out explicitly or not. So y prime is equal to y squared over 2x squared plus xy. This is clearly a homogeneous equation. Both the denominator and the numerator are homogeneous polynomials of degree 2. So the equation is of homogeneous type. Okay, so it looks like this is one of those that I did solve directly. I mean, fully. So I'm using these slides from last term. So this is old content from last term. So y is equal to ux. So y prime is equal to u prime x plus u. So these are the two formulas that you should actually know and know how to use when you're dealing with a homogeneous equation. And then you get that u prime x plus u is equal to, so what did we have here? So we had y prime becomes ux quantity squared over 2x squared plus x times ux, where the ux comes from the y here in the denominator. Okay, so now notice, and this is important, that now all the terms, both in the denominator and in the numerator, contain a factor of u squared. So here, ux quantity squared is equal to u squared times u squared. 2x squared, well, it's twice x squared. And x times ux is the same as u times x squared. So all the terms contain a factor of x squared. So this can be a second check that the equation actually is homogeneous, because if the equation actually is homogeneous, then at this step in the solution, all the terms should contain the same power of x squared. So since they contain the same power of x, so since they can all contain the same power of x, we can cancel it again when x is non-zero. So again, something special happens when x equals 0. So it's equal to, in this case, it's equal to u squared over 2 plus u. Right. So now, repeating the steps on the previous page, we want to isolate u prime. So we get that first, by subtracting u from both sides, we get that u prime x is equal to u squared over 2 plus u minus u. And then let's bring this fraction to a common denominator, because this will actually make the solution easier from now on. So u squared over 2 plus u quantity minus u is equal to u squared minus u times 2 plus u over the same denominator. So it's equal to u squared minus 2u minus u squared. The u squared cancels. So it is, I mean, whatever, still divided by the same denominator. So it is minus 2u over 2 plus u. Okay. So we're left with 2u in the numerator and the same denominator, 2 plus u. So now, dividing both sides by x, we finally get u prime by itself. So u prime is equal to minus 1 over x times 2u over 2 plus u. Okay. So we recognize that this is a separable equation because we have that u prime is equal to the product of a function of x and a function of u. Namely, minus 1 over x is a function of x, and 2u over 2 plus u is a function of u. But of course, you don't have to group them like this. You can also write it as 1 over x, which is a function of x, times minus 2u over 2 plus u, which is a function of u, or whatever, in infinitely many ways. So, right. So here I chose to write it as u prime is equal to minus 1 over x times 2u over u plus over 2 plus u. So clearly this is a separable equation. So now let's separate it. So in order to separate it, we need to bring the terms containing u back to the side, sorry, the factors containing u back to the side containing u prime. So in order to do that, we multiply the equation by 2 plus u over 2u. So notice that this is not homogeneous, it's only separable, whatever. So we have that u prime times 2 plus u over 2u, or whatever, u prime times, so 2 plus u over 2u times u prime, as it's written here, is equal to minus 1 over x times, and 2u over 2 plus u here cancels the 2 plus u over 2u here, and 1 gets 1. So we don't need to write the 1 because product by 1 is the same. So 2 plus u over 2u times u prime is equal to minus 1 over x. So sorry for the, for skipping a number of steps, but I'm sure you can reconstruct them by yourselves. Okay, so now let's see how much time do we have. It's 10:20, we still have 5 minutes. Let's at least finish this example. So 2 plus u over 2u times u prime is equal to minus 1 over x. Okay, so integrating both sides as functions of x, we get that integral of 2 plus u over u prime dx is equal to the integral of minus 1 over x dx. So it's important to write the dx, dy, whatever infinitesimal you're using. So infinitesimal notation is important. So here we're integrating as a function of x. So we should put the symbol dx on both sides. Now u prime dx is the same as du by the substitution rule. I mean by the substitution rule for integrals. So we can write it as integral of 2 plus u du. The integral of the right-hand side, namely the integral of minus 1 over x dx, well, we already know how to compute it. It's minus natural log of absolute value of x plus a constant. What about the integral of 2 plus u du, which was obtained by replacing u prime dx by du? Well, so this is equal to integral of 2 over u plus 1, because this 2 plus u over u is equal to 2 over u plus u over u, and u over u is 1. And then, so it's integral du, and integral of 2 over u du is twice natural log of absolute value of u. Integral of 1 du is u, and then it's plus another constant because antiderivatives are only unique up to a constant. So, and the constants C1 and C2 may be, but need not be the same. Okay. So, all right, now, again, we don't need to keep both constants, we just need to retain their difference. So subtracting C1 from both sides, one gets that 2 natural log of absolute value of u plus u is equal to minus natural log of absolute value of x plus C3, where C3 is the difference of C2 and C1. Okay, so unfortunately at this stage, I can already tell that we are not going to be able to solve this equation explicitly for you. So we are only going to be able to solve this equation implicitly for you. So this is the implicit solution of the equation in terms of u. However, we want to solve it in terms of x, not of u. So let's at least do this extra step. Namely, let's obtain the implicit solution as a function of y and x. So let's replace u back by what it was. So it was y over x. So then natural log of absolute value of u is natural log of absolute value of y minus natural log of absolute value of x. So we get 2 times this plus y over x is equal to minus natural log of absolute value of x plus C3. So this is the solution in implicit form. And we cannot go any further to make it explicit. However, of course, we can still do algebraic manipulations to make it look nicer. Like, for example, we can, whatever, add natural log of absolute value of x to both sides and multiply both sides by x and stuff like that. But of course, that's still not going to make the solution explicit. So let's see, when we multiply it by 2 plus u over 2u, so here, when we multiply it by 2 plus u over 2u, in order to make the equation separable, we implicitly assume that u is non-zero. So we implicitly assume that y is non-zero. So y equals 0 is another possibility that we must keep track of. So both x equals 0 and y equals 0 are possibly special for this equation. And it turns out that the constant function y of x is equal to 0 is also a solution, as you can check. And by the existence and uniqueness theorem, which we have not studied yet, it is the unique solution that will correspond to the initial value 0. Okay, so maybe one more very quick example. Well, now we are exactly at time, but I think it's 5 to go, 5 minutes over time since we started 5 minutes late. So all the terms in the, so let's first have a look at what the equation actually is. Y prime is equal to x cubed plus y cubed over xy squared. So all the terms, both in the denominator and in the numerator, have degree 3. The numerator is a polynomial. The denominator is a monomial. So the equation is of homogeneous type. Now, let y be equal to u times x. So y prime is equal to u prime x plus u. Okay. So this is again the substitution that you must always use. And the second part follows by the Leibniz rule. And then making these substitutions into the equation, I get u prime x plus u on the left-hand side is equal to x cubed plus ux quantity cubes over x times ux quantity squared. And we cancel the x cubed from both the x cubes from both the denominator and from the numerator. And we are left with 1 plus u cubed over u squared, which is 1 over u squared plus u. Now the u cancels from both sides of the equality, and we're left with u prime x is equal to 1 over x squared. This is a separable equation, and now let's separate it. So in order to separate it, we should multiply by u squared and divide by x, and we'll get u squared u prime is equal to 1 over x. Now the equation has been separated. And now integrating both sides with respect to x, we get integral of u squared u prime dx is equal to the integral of 1 over x dx. U prime dx is the same as du by the substitution rule for integrals. And then we get that u cubed over 3 is equal to natural log of absolute value of x plus a constant, where the constant is the difference of the constants that you get from each antiderivative, like I said before. And then u cubed is equal to 3 times natural log of absolute value of x plus another constant c2, which is thrice c1. And then u is equal to 3 natural log of absolute value of x plus c2 quantity to the power 1/3. So the cubic root of a real number is always well-defined and uniquely defined. So it's fine to take cubic roots of all real numbers. Okay. For complex numbers, it's a bit more complicated. So y of x is equal to 3 times natural log of x over of x plus c2, everything raised to the power 1/3, which is the same as taking the cubic root, and then quantity times x. And all right, so this is a pretty explicit solution. Let's see, did we miss anything? I don't even know. Probably we should check for whatever happens in the special cases when x is 0 or y is 0. So we need to check for what happens there. And now let's do an initial value problem. So let's consider the previous equation together with the initial condition y of 1 is equal to 2. So because we started at 1, which is bigger than 0, probably the maximal domain of existence of the solution will be the half line 0 infinity. Probably again something special happens at 0. Why does something happen special, or why may something special happen at 0? Is because we are dividing y cubed by xy squared here. So y squared cancels and we are left with y over x. Well, we don't always know whether we can divide y by x, so we have to pay attention at 0. And what else? So something special could also happen if y were 0, because we are also dividing x squared by y squared here. So in any case here, neither the initial value of x nor the initial value of y is 0. So we can just go ahead and solve the problem. And we have already seen the general solution, well, whatever disregarding whatever particular cases I just mentioned. So we have already seen the general solution on the previous page, and it is 3 times natural log of absolute value of x plus c2 quantity to the power 1/3 times x. And now we have to compute the constant c2, plugging in 1 for x and 2 for y. So these are given by the initial condition. We get 2 is equal to 3 times natural log of absolute value of y, which is 0, plus c2 raised to the power 1/3 times 1. Times 1 doesn't matter. So this is 2 is equal to c2 to the power 1/3, which means that c2 is equal to 2 cubed, so c2 is 8. So the solution of this initial value problem is 3 natural log of absolute value of x plus 8 raised to the power 1/3 quantity times x. And then since we are really only solving this for positive x, we could drop the absolute value. So this would be 3 times natural log of x plus 8, everything raised to the power 1/3 times x. And okay, and more than this, we cannot probably do today. We're already much over time. Again, sorry for this. It's my fault. And so the last example here is left as an exercise. Of course, we can do it in class next time, or we can do it during office hours, or we can do it whatever, or whenever, or you can email me about it, or yeah, anyway, or you can just think about it yourselves without asking for my help. And all right, thanks again for your attention. So this concludes today's class. Please let me know if you have any questions or comments.
Thank you, Professor.
Thank you.
All right.
Have a good weekend.
Thanks, Trey. All right. You too. All right. See you on Monday.